bit loud. Okay, so I think, is this the last chapter? I think so. I mean, the last big one. The rest, not too bad, really. All right, I'm looking forward to this one. Chapter 7, Functions. This is one of the most demanding chapters in the book. At its end, we'll have implemented functions and function calls, complete with local bindings and function call arguments. But to get there, we have to do a lot of thinking and make many tiny changes that look innocent but have a great impact on our monkey implementation. We'll come across more than one challenge along the way, because you see, the problem with implementing functions is this. It's not just one problem. The first one is the question of how to represent functions. The naive assumption is that functions are a series of instructions. Yeah, I mean, that was my assumption. But in Monkey, functions are also first-class citizens that can be passed around and returned from other functions. Okay, but that's like a future problem. How do we represent a series of instructions that can be passed around? Interesting. I think he might have just given a hint there. How do we represent a series of instructions that can be passed around? I mean, I would say, like, if I had to do it, I would do it the same way arrays are done. Like, they point to a region of the stack. But functions would be a region of the instructions. That would be how I would do it if I had to. Once we answer that, there's the issue of control flow. How do we get our VM to execute the instructions of a function? And let's say we manage to do that. How do we get it to return back to the instructions it was previously executing? Yep. And while we're at it, how do we get it to pass arguments to functions? Yeah. We'd have to maintain, what's the word? You know how the current stack is like global? Not sure. While we're at it, how do we get it to pass arguments to functions? These are the big questions, followed by a myriad of smaller ones that are hard to ignore. Rest assured, we'll answer all of them, just not all at once. Instead, we're going to weave many different parts into a coherent whole by taking well-considered baby steps, which is also what makes this chapter incredibly fun. Okay, dipping our toes, simple function. Our goal for this first section is to only get this seemingly simple piece of monkey code compiled and executed. Okay. This function has no parameters. It doesn't use local bindings. It's called without arguments and doesn't access global bindings. While I'd wager that there aren't many highly complex monkey programs in existence, this one is definitely one of the simpler ones. Still, it poses multiple challenges. Represent in functions. I mean, if I were to go based on what we have right now, this is kind of similar to, not exactly, but accessing elements of an array. Somewhat. This is a let statement. Yeah, but yeah, I have no clue. How do we represent functions? What is a function? It's like scoped series of instructions. I mean, just this one, without any arguments. Before we can even think about compiling or executing this function, we run into the first challenge. How do we represent functions? We know that a function consists of monkey code. We also know that we compile monkey code to monkey bytecode. Yep. It follows that a compiler should turn functions into at least a series of monkey bytecode instructions. The question is then, where do we store the series of instructions and how do we hand it to the VM? We already pass the instructions of the main program to the VM. We can't just mix those with instructions of a function. If we did that, we would have to untangle them again in the VM in order to execute them one by one. It's best to keep them separate from the start. Okay. The answer to our question lies in the fact that monkey functions are monkey values. They can be bound to names, returned from other functions, passed to other functions as arguments, and much more. Just like any other monkey value. And like other values, they're also produced by expressions. Yep. These expressions are the function literals, the literal representation of functions in monkey code. Yep. Hang on, my chair. Oh no, I thought it was sinking. The curious thing about function literals is that we have The value they produce doesn't change ever. It's constant. Yeah. Treat function literals like other literals that produce constant values and pass them to the VM as here it comes constants. Function literals. Okay. We'll compile them into sequences of instructions and add them to the compiler's pool of constants. An op constant instruction then takes care of putting the compiled function onto the stack. Okay, just like a value. Now, the remaining question is how to exactly represent these sequences of instructions so they can be added to the constant pool and loaded onto the stack. Yeah, okay. In writing an interpreter in Go, we defined object of function, a monkey object that represents evaluated function literals, which itself can be evaluated. The updated version of that function object, a function that holds bytecode instead of AST nodes. For that, we open up our object package and introduce the new object.compiled function. Okay. Contains instructions. Okay. Object.compiled function is everything we need. Can hold the code. Dot instructions we get from the compilation of a function literal, and it's an object, which means we can add it as a constant to our compiler or bytecode. Opcodes to execute functions. First question we have to ask ourselves is whether we need new opcodes to achieve our goal of compiling and executing the snippet of monkey code from above. Let's start with what we don't need. An opcode for function literals, since we decided to compile them to Object.compiled functions and treat those as constants. They can be loaded onto the stack of the VM with our existing opconstant instructions. How would that work? Ah, right. Okay, I see. We have global bindings in place, and they work with any object.object. But we do need an object opcode for the second line. That's a call expression represented by an AST like so. And it must be compiled to an instruction that tells the VM to execute the function in question. If we don't have an opcode that fits this needs, we need to define a new one. It's called opcall and doesn't have any operands. Okay, yeah. Ah, I see why. We don't need an opcode for this statement now. Because it's not really executing anything. It's more for compilation. Okay. Here's how it'll be used. First, we get the function we want to call onto the stack. For example, with an opconstant instruction. Right. Then we issue an opcall instruction that tells the VM to execute the function on top of the stack. Okay. This little instruction manual for opcall is what's called a calling convention. Once we add support for function call arguments, it will have to change, but for now, it's just 2 steps. Put the function you want to call onto the stack, issue an opcall instruction. Okay. With opcall defined, we are now in theory able to get a function onto the stack of our VM and call it. We still need is a way to tell the VM to return from a called function. More specifically, we need to differentiate between 2 cases where the VM has to return from a function. The first case is function actually returning something implicitly or explicitly. The second one is when the execution of a function ends without anything being returned. Right. Let's talk about the former case, the explicit and implicit returning of values. Monkey supports both. Yeah, because this will get maybe. An explicit return statement stops the execution of the rest of the function and returns the value produced by the expression following the return keyword. In the case above, that's the infix expression 5 plus 10. Without a return statement, a function call evaluates to the last value produced inside the function. That's what's called implicit return. The evaluator we built in writing an interpreter. The implicit returning of values was the default case. Explicit return statements were an additional feature we had to build. This time, though, the implicit return will be a slight variation of the explicit return. But in other words, these two will compile to the same bytecode. Right, okay. But it also means we have to implement both mechanisms in order to get the 5 plus 10 function from above compiled and running. In order to get 5 plus 10 function from above compiled and running. No shortcuts. Even if we only use implicit returns. With this increased effort in the compiler now, will make things a lot easier in the VM later on. Since they both compile down the same bytecode, implicit and, I mean, to be honest, I don't really care about the implicit return. They're both, excuse me. Since they both compile down to the same bytecode, implicit and explicit returns will also be represented by the same opcode. It's called op return value and tells the VM to return from the function with the return value. Interesting. Yeah. Doesn't have any arguments, as you can just use the stack, well, the topmost value on the stack. It's clear when and how to emit this opcode in case of explicit returns. Implementing implicit returning of values takes slightly more effort. Well, we just check if the last statement is a return. If it was the last executed statement in a function's body, we previously made sure that an expression statement does not leave a value behind, yeah or yeah, because it gets popped off the stack. For now though, put this issue, yeah, I think this is not a big deal. You can just not support implicit return. I know, I never really liked it. Talk about the second and much rarer case when returning from a function. A function returning nothing. See, this becomes a challenge because we support implicit returns. If you didn't support implicit returns, this is not a problem either. Quite tempted to not support implicit return. Since nearly everything in Monkey is an expression that produces a value, right? That's a function with an empty body. Doesn't have any instructions. Local bindings. Yep. Granted, a function that returns nothing is an edge case. Yeah, we'll see. I probably just won't support it. No implicit returns. Since a function call is an expression and expressions produce values to be consistent, these functions too produce a value. We could ignore the whole issue by putting it in front. Found a new scar on my leg. Since a function call is an expression and expressions produce values, to be consistent, these functions too should produce a value. Could ignore the whole issue by putting it in a file called undefined behavior and call it a day. Or we could make these functions return object.null. It does make sense for a function that didn't produce a value to return it. Yeah, I mean, seems like quite unnecessary, all of this. So there's another opcode. Yeah. I don't know. We'll see. Compiling. Function literals. Object.compiled function to hold the instructions of a compiled function and then pass them from the compiler to the VM as part of the bytecode. Yep. Yep, op call, op return. Yeah, I think I'm just gonna have op return without the implicit return. That's enough for us to start compiling, but again, baby steps. Before we can start compiling a function call, we're going to make sure that we can compile the function being called. That gives us a clear first task: compile function literals. A function without arguments, integer arithmetic in the body, and an explicit return statement. Yeah, hang on, yeah. A constant, and then op return, and then want to say it's a call expression. Where's the add? And in the main program contained in bytecode.inst. Ah, fuck. Okay, these are just constants. Interesting. Would it be a slice of constants? And in the main program contained in bytecode.instructions, we need an op constant instruction that loads this function onto the stack. Okay, interesting. Not sure how this works yet. Why is it and in an instruction? First glance, it doesn't look like there's anything new in this test, but expected constants now also includes a slice of code dot instructions. Oh, interesting. So these are just constants. Okay, I missed that bit. Okay. I still don't get it. These are the instructions we want to see in the field for object.compiled function, which is passed around with an index 2. Code dot instructions. All right, okay, gotcha. You check it against function instructions. Okay, I missed that bit. Okay. Beautiful, yeah. Interesting. It's gonna be a bit of a challenge. Because if I have a look at constants, slice of object dot object. Yeah, I don't know. This might be a lot more work than anticipated. The body of an AST.function literal is an AST.block statement. Contains a series of AST statements. Yep. Since we already know how to compile AST.block statements from compiling, yep. Compiling statements in a function's body shouldn't be a problem. But if you were to simply call the compile method with the body of function literal, we'd end up with a mess. The resulting instructions would end up being entangled with the instructions of the main program. Introducing our compiler to the concept of scopes. Sounds quite elaborate, but it's actually a straightforward change. In practical terms, it means that instead of using a single slice and two separate fields Last instruction and previous instruction. Never really added this, to be fair. How did I end up doing it? Yeah. I just keep track of the position. Okay. It means that I don't even remember this one. The emitted instruction. I forgot what it was for. If never use it though. It's weird. I know I do use it. I can't remember where. Anywho. Bundle them together. Compilation scope and use a stack of compilation scopes. Okay, so this is new. Scope index. Before we start compiling a function's body, that is, enter a new scope, we push a new compilation scope onto the scope stack. While compiling inside the scope, the emib method of the compiler will modify only the fields of the current compilation scope. Once we're done compiling the function, we leave the scope by popping it off the scope stack and putting the instruction. I'm getting a bit confused. Can't see how it all goes together. Probably why. compiling inside the scope, the emit method of the compiler will modify only the fields of the current compilation scope. I could read that again. I'm a bit distracted. Before we start compiling a function's body, i.e. enter a new scope. Okay, gotcha. While compiling inside the scope, the emit method will only modify the fields of the current compilation scope. Okay, now I get it. Once we're done compiling the function, we leave the scope by popping it off the scope stack and putting the instructions in a new object.compile function. Test compiler scopes. Get a new compiler. Emit one instruction. Compiler dot, oh fuck, okay, now I see. So I'm guessing scope 0 is like main. Okay. So when you call enter scope, you just move the index forward. Gotcha. Okay, that makes sense. What happens when you leave the scope? Because you mentioned something about object.compile function. Okay, I see. So when you leave this scope, you move all the instructions within that scope into that object, which has slice of instructions, into the constants, and then yeah, add an up constant. Previous instruction. Excuse me. Yep, it should be multiply because that was the first one. Okay, I think I get what scopes do. I still don't want to write any code yet because I'd like to understand how this all works together first. We test two new methods on the compiler here, enter scope and leave scope. I guess it's just moving index forward and backward. I suppose when you leave, you might have to push a constant onto the push the instructions onto the constant pull, which will be this thing, object.compile function. Okay, it's actually starting to make some sense now. Yep, they don't affect each other's scope. First we have to remove the instruction, last instruction and previous instructions from the compiler. Right, and then move them onto the scope. Okay. Excuse me. Actually not too bad. I guess when you come across a call expression, yeah, the last constant should be the list of instructions. Why not move the symbol table also to the compilation scope? Okay, I think this is gonna be shortest stream ever for a while. Mm-hmm. Mm-hmm. Okay, and I guess you gotta keep track of the scope index. It's gonna be a few changes. Because I didn't create any of these methods. I think I've inlined them. Just want to have a look at. Yep, returns instructions. Exactly what I thought. Why not include the last? Okay, you just remove. Yeah, I think that's fine. Okay. You get all the instructions. Okay, I think it's a problem for tomorrow. Go start. And call blah 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 here. I just wanted to show up today. I have been a bit lazy the last week. It was tough. I waited like I think an hour. Yeah, for an hour I was just sitting, just wondering if I should be streaming or not. Yeah, I'm glad I did. I mean, it's I haven't done anything, but I'm glad I showed up. Okay, I think fucking so my yeah, okay, I think that's it for today. I mean, it was pretty shit, but reflects how I feel inside. So yeah, I'll take that as a W. W for showing up. Right, have a good day, and I'll see you back here tomorrow with a better fucking hell. Something's in my eye. Yeah, whatever. Alright, yeah, see you tomorrow. Have a good one. Yeah, that's